SwayamPrabha. Digital India. Educated India.
Okay, so in the last class, we have discussed the Flory theory for good solvent, and we have been able to derive the scaling law for the self-avoiding walk, that is essentially R, that we can think of as square root of the ensemble average of the mean square gyration radius. We are doing a scaling theory in this case. So, this R scales like m to the power 3 by 5, and what we said was that if I now extend the idea to a bad solvent case, there is a problem, and the problem is we also had a v to the power 1/5 there, and the v can be negative in the bad solvent case. Actually, v is negative in the bad solvent case, and so we get like an imaginary value of R, which is not possible. And then what we said is we have to go back to the visual expansion and keep in mind that the 3-body interaction that we have ignored for the good solvent case will become important for the bad solvent case. So, we must include that, and now I will show you like how does it counter this particular problem and how do we get the scaling law for the bad solvent case. So, we are doing the Flory theory for the bad solvent or poor solvent. So, we again do the approximation that we made earlier, that the total energy is additive. We can add the elastic energy and interaction energy, but now in the interaction energy term, if you recall from what we derived in the visual expansion, we had powers of concentration starting from second power, so in the earlier case we only considered the first term, and now we will consider both first and second term, and we will see like what difference it makes. So, the earlier one was for V higher than 0, and now we do it for V less than 0. Okay. And we have given the argument that there will be more 3-body interaction when the chain is collapsed, simply because the number of contacts increase as we go to a collapsed chain. Okay. So, we again make the other approximations that we have made, that is my elastic energy, we take it to be same as that we have got for an ideal chain, and we still assume that the concentration C can be approximated as a uniform concentration where we ignore the connectivity of polymer segments, and then this becomes m by r cube. And now if I include the u int scales like k b t comes out, the integration over dr becomes r cube. We do not care about the prefactors, and then we have v, and then we have c square, that it becomes c tilde square, and that is m by r cubed whole square, and then we also have plus w, and we have c r to the power cube. So, first we have r cube from the integration of dr, and then m by r cube to the power cube, and so do we get which has to be added with the elastic energy term. Okay. So, in totality what we now have is the total energy of chain is sum of the elastic energy and the 2 body terms and 3 body terms. So, now you play a trick here, and the trick is that m is very higher than 1, okay, and that we already assume that the chain is very long. Okay. What also happens in the case of a collapsed chain is r is very small. Okay. So, if I look at the first term here, the first term will be very small compared to the other 2 terms, simply because it has m in the denominator, a larger quantity in denominator, others have m in the numerator, and also it has r in the numerator, r is small, others have r in the denominator, and so we can essentially drop the first term from here that we can do for the bad solvent case. So, essentially now the competition which was earlier for the good solvent case between the elastic energy and 2 body interaction is now the competition between the 2 body interaction and 3 body interaction for the bad solvent case. Okay. So, now you can note a few things here. The first thing is that both these terms are positive. If I assume the first term is always, so in this case the first term is negative because v is less than 0, and of course m and r are positive. We do not yet know about the sign of w, and we have to think of like what should be its sign, that we can get by looking at the dou u by dou r equal to 0, that is the energy minimization condition that we have used earlier. So, let us do the same thing we did earlier, keeping in mind that now the v is negative. So, this gives me again we do not care about the prefactors. Which gives me r cube is like w by v to the power m. Now, we have taken v to be less than 0, that means w also has to be So, in this case what we get is r cube is minus of this. So, if V is less than 0, then to make this R positive, W has to be higher than 0. Okay. That is a requirement that the 3 body term, the coefficient must be positive if the 2 body term coefficient is negative. Okay. If this is not true, then in that case we will not get a positive value of R. So, it must be true by this kind of an scaling theory idea. It turns out that it indeed is the case if I do a more rigorous derivation. Okay. So, if we keep that in mind, then we get R as minus W by V 1/3 m to the power 1/3, and essentially we have recovered the relation that we wanted to. So, now again comparing to the ideal chain, which was R square scaling as m, we have m to the power 2 by 3. 2 by 3 is less than 1. So, the chain is more collapsed compared to the ideal chain, and of course, the self avoiding walk that we have discussed earlier. Okay. So, to summarize what we have discussed for the good solvent case and bad solvent case, and also including the ideal chain we have derived earlier, we can write R in general to be like scaling like m to the power a coefficient nu, or m scaling like r to the power 1 by nu, where nu is equal to 1 by 2 for random walk or ideal chain, and is equal to 3 by 5, that is higher than 1 by 2 for self avoiding walk, that is swollen chain, and this is equal to 1 by 3 for collapsed chain. We can also talk in terms of V and temperature. So, the first case is realized when V is equal to 0. The second case is for V higher than 0. The third case is for V less than 0. So, the first case is for T equal to theta. The second case is for T higher than theta, and third case is for T less than theta, theta being the temperature where ideal chain behavior is established. Okay. So, now I want to take somewhat of a detour from here and talk about some other behavior of polymer chains, and we will come back to this particular scaling law that we have derived and see how exactly it tells something about the structure of the polymer chain. Okay. So, before we go into that, I want to take a small detour and talk about something that is known as self-similarity and something that is known as the fractal nature of polymer chain. Okay. So, let us talk about two other features of a polymer chain that it shares with many other objects. So, they are subjects of their own. We will very briefly describe both these features. The first one is self-similarity and second one is fractal nature. So, what self-similarity means is, if I zoom in into a polymer chain that is undergoing either an ideal chain like behavior like a random walk or a self-voiding walk or a collapsed chain, irrespective of like what condition that chain is, if I zoom into it, I will essentially see the same type of object because the number of segments are anyway huge. That means that if we look at a large polymer chain like this, and if I say zoom into a particular region here, I will still see the same thing, same kind of a polymer chain. Again, if I zoom into here, I will still see the same kind of a chain, right. So, do not really go by the scale here. So, we can change the resolution of our camera the way I am looking into it, and we will look at the same kind of structure at all scales, and this has happened because M is very large. There is another way to think about it. If I think of say a freely jointed chain model containing say 10,000 segments compared to the case of a freely jointed chain model containing of say 100 segments or 50 segments, they both look identical and show a similar scaling behavior. Okay. So, the scaling behavior, the way we look at the chain does not really change no matter how we or what resolution we look into through the camera. Okay. This is a feature that is unique to polymer chains and some other objects that they possess. It is not present in everything else. So, think of like, let us say if I zoom into a sphere or a disk. Okay. So, if I zoom in there, let us say if we have a disk, and if I zoom in there, maybe I will focus on a particular corner of the disk, and I will see maybe a structure that does not look like a disk anymore. And if I zoom in further, I will see something else. We can look at a particular edge, for example, of the disk. The same thing we can extend to any other shape, any regular shape. If I am zooming in, I am looking at a particular corner or edge or some part or some portion of the chain, and they will look very different than compared to the original shape that we started with. Okay. This is what makes polymers different. They have what is known as a self-similarity, that is independent of scale, independent of like where I look into it. The only idea is that the number of segments has to be very large. Of course, if I go to the level of say m equal to 1, then in that case we will look at the molecular conformations of carbons, and that will of course be different than compared to the case that we see for larger values of m. But provided m is large enough, we will look at the polymer chain as a Gaussian or the self-voiding random walk, and it will be somewhat independent of the scale and resolution. Okay. That is one feature that is very unique to the polymer chains and some other objects. The other feature is, if I look at the number of units or the number of atoms or particles present in the system at a distance r from a particular point, that shows a very particular scaling than compared to regular objects we are used to seeing. So, if I look at the number of say particles or constituents or segments at certain distance r, and let us call this as n of r. Then if I have a one dimensional object like a rod, then the more distance I cover, the more particles I will see in the object, and I can really say that the number will go like r. Okay. So, think of it like the rod is built up of segments like this, and if I count these segments, then the longer distance I look, the more particles or segments I will see, and it is simply proportional, that the number is proportional to the distance I am looking at. If I look at a 2D object, let us say if I look at a circle and I start from say the origin, and if I look at objects at a distance r, now you can very well expect that the number of things you will see will be proportional to the area. In this case, it is proportional to the length for one dimension, for 2D is proportional to the area, and so the number will go like r square. Other way to think about it is, in the one dimension case, I can think of a line density, and if I multiply the line density with the length, then we get the number of segments or units. In the case of 2D, we can think of a surface density, that is, we have to multiply the surface density with the area to get the number of units or objects or particles. Similarly, for 3D, let us say we have a sphere, the number of segments go like r to the power cube. So, in general, what we can say is, for solid objects, n of r goes like r to the power d, where d is the dimensionality. Okay. Now, if I look at the polymer chain, this behavior is not observed, because we have just derived in the previous class the scaling laws for the good solvent case, and we just discussed the scaling laws for the bad solvent case, and essentially this n of r correspond to our m in the scaling law, and if I look at that, then we have got r going like m to the power nu. So, m, that is equivalent of n of r, is going like r to the power 1 by nu, which is not the same as the dimension that we are working with. Okay. For example, for the ideal chain in any dimension, and this we have shown using the description of a drunkard walk in one dimension, he was going left and right, then still we got r going like square root of m. Then we did the case of a two dimensional walk on a lattice, we still got the same scaling law. We can do it for any z dimensional lattice, we still got the same scaling law. So, for an ideal chain of any dimension, nu 1 by nu is simply equal to 2, because nu is equal to 1 by 2. Okay. So, what we can then say for objects that do not have n r going like r to the power d with the dimension that we are working in, they are called a fractal, and in general they follow some other scaling that we can call the fractal dimension. So, now the fractal dimension of course is 1 by nu for the models we have discussed. So, it is equal to 2 for an ideal chain, it is equal to 5 by 3 for a self avoiding walk, it is equal to 3 for the collapsed chain, which at least for the 3D case is equal to the d. Okay. So, at least the first two can be considered the fractal. To be more specific, the ideal chain in 3D can be considered a fractal, an ideal chain in 2D has the df equal to d. In that case, we can consider it as not being a fractal. Okay. So, this is the idea we will build upon. So, before we go further into it, just like we have done for the ideal chain case, we looked at 1 dimension, 2 dimensions, and in general z dimension walks on a lattice. Let us see how the Flory theory helps us when we are trying to do a scaling law for a general d dimensional walk. Okay, so I will discuss that in the next class. So, thank you.